The enormous blast is an idea that has delineated how we could unravel the universe, addressing the assistance of stream cosmology, as per Einstein's theory, and what is known as cross-examining cosmology. The gigantic blast was the moment the universe started its expansion, marking the creation of all matter, energy, and existence. This event happened approximately 13.8 billion years ago and led to the vast universe we observe today. However, recent advancements in cosmology suggest that the epic blast probably wasn't the outright beginning. Rather, there might have been a phase before the massive impact that was also critical in shaping the universe as we know it. This pre-period is known as inflationary development. Inflation is one of the most fascinating aspects of modern cosmology. It suggests that before the hot, dense phase of the Big Bang, the universe underwent an extraordinarily rapid and dramatic expansion. During this period, the universe grew exponentially at an astonishing rate. To illustrate how extreme this growth was, if the universe started smaller than a particle, it would have expanded to be incomprehensibly larger than the entire observable universe within a fraction of a second, around 1/4,000,000th of a second. This growth phase didn't last long, but played a crucial role in shaping the universe. When the inflationary stage ended, the energy driving this expansion was released into space, heating it up and creating the particles of matter that form everything we observe today. In many ways, inflation is the precursor to what we consider the Big Bang. While the theory of inflation is widely accepted in cosmology today, many unanswered questions remain. For example, we don't yet understand what started inflation, what caused it to stop, or how long it lasted. These are open questions in cosmology, and answering them is vital for a deeper understanding of the universe's origins. Before inflation, the universe was an unimaginably dense, minute point of matter, often referred to as a singularity. From this singularity, inflation began and eventually led to the formation of atoms, particles, stars, and galaxies. The idea of the Big Bang as the origin of everything is compelling, but modern cosmology suggests a more complex picture. Some theories propose that the universe underwent a phase before the gigantic blast. During this stage, inflation caused the universe to expand at an extraordinary rate, increasing in size by an astounding factor within a trillionth of a second. This rapid growth was fueled by a peculiar form of energy that filled empty space. When inflation ended, the energy driving this expansion converted into particles, heating the universe and leading to the hot, dense state we call the Big Bang. This inflationary phase was cold and empty, yet it set the stage for the creation of matter and the universe we see today. One of the more speculative ideas in modern cosmology is the concept of eternal inflation. This hypothesis suggests that inflation didn't shut down all at once. Rather, it stopped in patches, creating different pockets, each of which could be a universe in its own right. Our universe would be just one of these patches. According to eternal inflation, there could be an infinite number of these universes, each with its own set of physical laws and constants. This is where the possibility of the multiverse comes into play, the idea that our universe might be just one of many, or even an infinite number of universes. If this idea is correct, it could explain why our universe is so finely tuned for life. In this multiverse scenario, every possible combination of physical laws could exist in different universes, and we just happen to live in one where conditions are perfect for stars to form and for essential elements like carbon and oxygen to exist. While theories like eternal inflation and the multiverse remain speculative, the concept of inflation itself is grounded in observational evidence. The strongest support for inflation comes from the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMB was created nearly 380,000 years after the Big Bang, when the universe cooled enough for particles to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. This light provides clues about the universe's earliest days, helping researchers understand what happened shortly after the Big Bang and supporting the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which captured detailed images of the CMB. These images reveal subtle variations in the temperature of the early universe, and these variations match predictions made by the inflationary theory. This experimental evidence strengthens the idea that inflation is not just a theoretical model, but a fundamental part of how we understand the universe's origins. Understanding the Big Bang and what happened before it requires combining two of the most important theories in modern physics: Einstein's theory of general relativity and quantum theory. General relativity describes the large-scale structure of the universe, including the behavior of galaxies, stars, and planets. Quantum theory describes the behavior of particles on the smallest scales. To address the big questions in cosmology, such as what the universe is made of and where it came from, scientists need to develop a theory that unifies these two systems. Such a theory wouldn't only help us understand the Big Bang, but also the conditions that led to it. One of the most astonishing aspects of the universe is its size. The most distant objects we can observe are around 47 billion light-years away, meaning the observable universe is about 94 billion light-years across. This might seem odd, given that the universe is only 13.8 billion years old. How could the observable universe be larger than the distance light could travel in its lifetime? This intriguing question is answered by how the universe has been expanding over time. As the universe expands, the distance between objects increases, making distant objects farther away than the time it would take light to reach us. Most scientists accept that the universe extends far beyond the observable universe. In fact, it's possible that the entire universe is infinite in size. The observable universe is only the portion we can see, limited by how long light has had to travel since the Big Bang. There might be vast regions of the universe that we will never be able to observe. While it's possible that the universe is infinite, the question remains: is there anything beyond the universe? The question of what lies beyond the universe is one of the greatest mysteries in modern cosmology. If the universe is infinite, it might extend endlessly without any boundary. However, if the universe is finite, there could be regions beyond our observable limits that we cannot reach due to the finite speed of light and the constant expansion of space. Some theories suggest that if we could somehow venture beyond the observable universe, we might find regions governed by entirely different physical laws or constants. These regions could be vastly different in structure, composition, and behavior from what we are familiar with. This idea aligns with the concept of a multiverse, where our universe is just one of many. Other speculative ideas propose that what we perceive as our universe could be part of a higher dimensional structure. In this view, our universe might exist as a three-dimensional brain within a larger multidimensional space. Theoretical frameworks like string theory and M-theory explore these possibilities, suggesting that our universe may interact with other universes or dimensions in ways that are currently beyond our comprehension. Additionally, some cosmologists hypothesize that the universe might eventually loop back on itself, creating a finite but unbounded cosmos. In this model, if you were to travel far enough in one direction, you could theoretically return to your starting point, much like traversing the surface of a sphere. The end of the universe. Just as the origins of the universe remain a profound mystery, so does its ultimate fate. Current observations suggest that the universe is expanding at an accelerating rate, driven by an enigmatic force called dark energy. This acceleration raises questions about how the universe will evolve over billions or trillions of years. There are several possible scenarios for the end of the universe. 1. Heat death, big freeze. If the expansion continues indefinitely, the universe may cool down as galaxies move farther apart, stars burn out, and matter becomes increasingly sparse. In this scenario, the universe would reach a state of maximum entropy, where no useful energy remains to sustain processes like star formation or life. 2. Big crunch. If the expansion eventually reverses due to the pull of gravity, the universe could collapse back in on itself. This would result in a big crunch, where all matter and energy are compressed into a singularity, potentially leading to another Big Bang and the birth of a new universe. 3. Big Rip. If dark energy's influence grows stronger over time, it could tear apart galaxies, stars, planets, and even atomic structures. This catastrophic end, known as the Big Rip, would disassemble the very fabric of space and time. 4. Vacuum decay. A more speculative idea involves the possibility of a metastable vacuum state. If the universe is not in its lowest energy state, a quantum fluctuation could trigger a transition to a true vacuum. This event, known as vacuum decay, would propagate at the speed of light, fundamentally altering the universe's structure and rendering it uninhabitable. Bridging the unknown. Understanding the origins, evolution, and ultimate fate of a universe requires uniting quantum mechanics with general relativity into a comprehensive theory of quantum gravity. Such a theory could provide insights into the conditions that gave rise to the Big Bang, the nature of dark energy, and the mysteries of black holes and singularities. Advances in observational technology, such as next-generation telescopes and detectors, are also crucial for unraveling these mysteries. For example, the James Webb Space Telescope is already providing unprecedented insights into the early universe, and future missions may further illuminate its most enigmatic phases. Ultimately, the study of the universe is not just about understanding its physical properties, but also about addressing profound philosophical questions. Why does the universe exist? What is our place within it? And are we alone in this vast cosmic expanse? While many questions remain unanswered, each discovery brings us closer to understanding the cosmos and our role within it. As we continue to explore, the story of the universe evolves, revealing new chapters in the grand narrative of existence. Universes. In the event that this thought is right, it could make sense of why our universe is so finely tuned for life. In this multiverse situation, each conceivable mix of actual regulations could exist in various universes, and we end up residing in one where conditions are ideal for stars to shape and for fundamental components like carbon and oxygen to exist. While hypotheses like everlasting expansion and the multiverse stay speculative, the idea of expansion itself is grounded in observational proof. The most grounded help for expansion comes from the enormous microwave foundation radiation, CMB, the most seasoned light known to man. For particles to shape by then, the universe became straightforward, and this light has been going through space from that point onward. By concentrating on the CMB, cosmologists can basically take a child image of the universe. This light gives hints about the universe's earliest days, assisting specialists with understanding what happened not long after the huge explosion and supporting the inflationary model. One of the main revelations came from the European Space Organization's Planck satellite, which took definite pictures of the CMB. These pictures uncover unpretentious varieties in the temperature of the early universe, and these varieties match expectations made by the inflationary hypothesis. This exploratory proof reinforces the possibility that expansion isn't just a hypothetical model, but an essential piece of how we comprehend the universe's beginnings. Understanding the enormous detonation and what occurred before it requires joining two of the main speculations in present-day physical science: Einstein's hypothesis of general relativity and quantum hypothesis. General relativity portrays the enormous scope design of the universe, including the way of behaving of universes, stars, and planets. Quantum hypothesis depicts the way of behaving of particles on the littlest scales. To resolve the unavoidable issues in cosmology, what lies under the surface for the universe and where it came from, researchers need to foster a hypothesis that consolidates these two systems. This wouldn't just assist us with understanding the enormous detonation, but also the circumstances that prompted it. One of the most surprising parts of the universe is its size. The most far-off objects we can notice are around 47 billion light-years away, meaning the recognizable universe is around 94 billion light-years across. This could appear to be odd, given that the universe is just 13.8 billion years of age. How should the discernible universe be larger than the distance light could go within its lifetime? This entrancing inquiry has an answer. It lies in how the universe has been expanding over time. As the universe grows, the distance between objects increments, making far-off objects farther away than the time it would take light to contact us. Most researchers acknowledge that the universe stretches out a long way beyond the perceptible universe. As a matter of fact, it's conceivable that the whole universe is limitless in size. The detectable universe is just the part we can see, obliged by how long light has had to travel since the huge explosion. There may be tremendous regions of the universe that we will never be able to see. While it's conceivable that the universe is boundless, the inquiry remains. Is there anything beyond the universe? Most experts have questions about this thought. Assuming the universe is boundless, there would be no outside to it. The universe would just proceed ceaselessly. Whether the universe is confined, it seemingly wouldn't make sense to look for anything beyond it. Beyond would suggest something beyond space, which itself is a property of the universe. So the possibility of beyond the universe presumably has no veritable meaning. Similarly, as the beginning of the universe is a subject of extraordinary interest, so too is its conceivable end. The best momentum gauge is that the universe will keep on growing perpetually. This is because of a perplexing peculiarity known as dark energy, which is making the universe's expansion accelerate. Before the discovery of dark energy, scientists accepted that the universe's expansion would eventually slow down due to the gravitational pull of matter. There was even a likelihood that the universe could stop expanding and start contracting, leading to a big crunch. However, dark energy seems to be pushing the universe apart more quickly. Assuming this speed increase proceeds, the universe will continue to grow endlessly. Eventually, universes will be so far apart that they become detached from one another. In this situation, the universe would grow cold, dark, and dead. Stars would burn out, galaxies would drift apart, and matter would ultimately decay. This is sometimes called the Big Freeze or the heat death of the universe. The tale of the universe, from the enormous detonation to its conceivable end, is perhaps one of the most significant and complex stories in science. While we've learned a fantastic amount about the universe's origins through the theory of expansion and the investigation of the CMB, many questions remain unanswered. What caused the expansion to start? How might it end? What lies beyond the noticeable universe? Is there a multiverse? And if so, how many different universes exist? As researchers keep on concentrating on the universe using cutting-edge technology and theories that combine quantum mechanics with general relativity, we are certain to gain further insights into these mysteries. The journey to understand the universe is ongoing, and each discovery brings us closer to answering the ultimate questions about our existence. The investigation of the universe's origins and structure isn't simply a scientific undertaking. It also raises philosophical questions about existence, reality, and our place in the cosmos. One significant area of interest in cosmology is the concept of dark matter, believed to make up around 27% of the universe's mass-energy content. Unlike traditional matter, dark matter doesn't emit, absorb, or reflect light, making it invisible and perceivable only through its gravitational effects on visible matter. Understanding dark matter is vital for making sense of the development and behavior of galaxies. Ongoing examinations and observations have provided insights into dark matter's properties, yet its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and other exotic particles. However, so far, no direct evidence of dark matter particles has been found. The search continues through a combination of terrestrial experiments, astrophysical observations, and simulations modeling how dark matter affects the cosmic scale structure of the universe. Another key area of research is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy accounts for around 68% of the universe's total mass energy content. Its discovery was unexpected and has led to various theories, including the cosmological constant and dynamic fields. Understanding dark energy is critical, as it will determine the ultimate fate of the universe. Scientists are studying its effects on cosmic structures and trying to determine whether it remains steady over time or evolves. The exploration of the universe's origins, structure, An ultimate fate is a rich tapestry of scientific inquiry and philosophical reflection. From the fundamental forces, the study of the universe also intersects with other scientific fields, such as astrobiology and particle physics. Astrobiology seeks to understand the potential for life beyond Earth by studying the conditions necessary for life to exist. Recent advances in the discovery of exoplanets, planets orbiting stars outside our solar system, have revealed thousands of potential candidates. Some of these exoplanets lie in their star's habitable zone, where conditions may allow for liquid water to exist, a key ingredient for life as we know it. By studying these distant worlds, scientists hope to learn more about the factors that make a planet habitable and to determine if life might exist elsewhere in the cosmos. The search for extraterrestrial life is not just a scientific endeavor, but also a philosophical and existential one, raising profound questions about humanity's place in the universe. In addition to searching for life, scientists are working on developing a unified theory of physics, one that combines Einstein's general relativity with quantum mechanics. Such a theory could explain phenomena like black holes, which are regions of space where gravity is so strong that not even light can escape. Understanding black holes is crucial, as they are believed to play a key role in the formation and evolution of galaxies. One leading candidate for a unified theory is string theory, which posits that all fundamental particles are tiny vibrating strings. Another is loop quantum gravity, which attempts to describe the quantum properties of spacetime itself. These theories, though still speculative, aim to bridge the gap between the largest structures in the universe and the smallest particles that make them up. As technology continues to advance, our ability to observe and interpret cosmic phenomena improves. Space telescopes like the James Webb Space Telescope are providing unprecedented views of the universe, from distant galaxies to the atmospheres of exoplanets. These observations not only refine our understanding of the universe's history and structure, but also inspire new questions and hypotheses. Ultimately, the study of the universe is as much about asking questions as it is about finding answers. It challenges our understanding of reality and pushes the boundaries of human knowledge. As we continue to explore the cosmos, we deepen our appreciation for its complexity and beauty, while gaining a clearer sense of our place within it. The universe is vast, mysterious, and ever-changing. Its story is far from complete, and the journey to unravel its secrets is one of the greatest adventures of human discovery. Whether through groundbreaking discoveries or philosophical reflections, our exploration of the cosmos is a testament to the enduring power of curiosity and the limitless potential of the human spirit.